All right, so on this one, we now have the same masses, but the different circumstance. The 9 kilogram mass is pulling the system in a direction, and the 5 kilogram mass is now on a platform that we need to account for friction. In fact, one thing we need to find out in this problem is the coefficient of kinetic friction. What else are we given? We're given that the acceleration of the system is 4 meters per second squared. Okay, so first things first, we are going to set ourselves up with an F net of the system to find out, well, let's see what that will give us. What are we trying to find out when we do that? All right, so we're going to have the gravitational force pulling downward, right? That is what is accelerating or generating the motion of the system. We know that the tension force here and the tension force here cancel each other out, and they're internal, so they don't appear in the F net of the system. They're not affecting it. And so what is the takeaway force? Unlike before, it's not the gravitational force, and it's not the normal force, right? Those two are also canceled out here, and not in the direction of motion. And so that's not the force we're looking for. What is the opposite directed force here is, of course, the force of friction. So we could plug in our numbers and we can actually solve for the value of the force of friction and then unlock the coefficient of friction. All right, so rearranging some for the frictional force, we're going to have the gravitational force of the 9 kilogram, 9 times 9.8, and the net force of the system. Remember, we're working with the system here, both masses. And so that's why I have 14 in a bigger number so that you know I wanted you to pay attention to that. That was not one or the other mass, that is the mass of the system. And of course, we were given 4 as the acceleration of the system. And so the frictional force is 32.2. And now let's also recall a formula for frictional force. Frictional force is, of course, the coefficient of friction times the normal force. And so what is normal force? Well, we can see on our diagram here is equivalent to the value of the gravitational force in this circumstance on that horizontal surface. Just doing some algebra, rearranging for the coefficient of friction. It is the frictional force divided by the normal force of that 5 kilogram mass. I wrote 5 in red, but then I wanted to make it big so it stood out in a different color, and I just wrote 5 on top of that. I think I just made it look a little messy in doing so. But nonetheless, when we do this and we crunch the numbers, it comes out to be... And what's the units to the coefficient of friction? There are none. It's a force divided by a force. A Newton divided by a Newton. Units cancel out, and it's just a value, 0.66. We're not done yet. We now want to find out what the tension force is, okay? Now, we could have done this right from the get-go since we already knew the acceleration of the system and thus the acceleration of each individual object, right? So let's just take this guy here and solve for the tension force. So when we don't look at a 2-body system, but just a 1-body system, we'll take a look at the forces acting on it. Now we can include tension force because since it's a 1-body system, it's not being canceled. And so these two forces come together to make this mass accelerate. And so let's put that together. Plugging in the numbers, rearranging, and doing our algebra appropriately, we find that the tension force is 52.2 newtons. Now, I just want to do one last thing. If that is true, and we know all the forces now acting on the 5 kilogram mass, we should be able to set up an equation that is a true statement. So let's do that. On the 5 kilogram mass, we know that the net force is going to be due to the frictional force pulling one way. We already said the frictional force is 32.2. And pulling to the right on that mass is going to be the tension force. And they come together to make that mass accelerate. So let's see if it's true when we put in all the numbers. When we put in the frictional force, and we add the tension force, does that equal the mass accelerating at 4 meters a second? And sure does. 20 equals 20. Check.